Welcome back. Good morning, good afternoon, good evening, wherever you're in the world. And today we are now in week 4 of the program. We are in day 10, and we're almost halfway through the program. It's going by so fast. So today we have a very special session planned for you. This week, we already had a very intense session on Monday talking about how do we solve differential equations on quantum computers, and then there was a change of pace. We talked about quantum entrepreneurship, and we did a lab tour on Wednesday. So today we are kind of diving again back into the technical focus area of this summer workshop. And today we're going to be talking about block encoding. So this is one of the key concepts that is fundamental to any quantum algorithm. If you pick up any paper on quantum algorithms, you would see these words being thrown about: oracles, linear combination of unitaries decomposition, block encoding. These are like techniques to that serve as data access models for a given matrix. And today, in order to talk about this, we have with us Guilermo Alonso-Linaje. Guillermo is an expert on. Guillermo is an expert from Xanadu. He's an expert specializing in quantum machine learning and algorithms. Not only is he an expert on the research side, he also has experience serving as an educator in quantum computing and is a perfect person to teach us about this exciting topic. And some fun facts about Guillermo: he is an expert playing foosball, and he calls himself a paella of quantum computing. You should ask him more about that later. And welcome to the program, Guillermo, and over to you.
Thank you very much for the presentation. I'm going to start sharing the screen. Okay, I hope you can see it.
Yes.
Can you see it? Okay, perfect. Thank you very much. Yeah, so I think to start, it would be nice to mention why I'm familiar with this particular topic. And when I've been working in different projects in Xanadu, and one of the biggest ones I've been doing this year is what we call the Quantum Algorithm Toolkit. That basically the idea of that project was to work in the main quantum algorithms, let's say quantum phase estimation, amplitude amplification with all the variants, quantum signal processing algorithms. And we were trying to detect what are the main building blocks. So we find those building blocks, then we try to optimize them and include them in Penny. And one of the main takeaways of that particular project is how important was block encoding. That is one of these technique that for some reason maybe is not the one that you learn when you are starting quantum computing, but again appears everywhere. And also in a more recent project, in a collaboration with Rolls-Royce, Xanadu Rolls-Royce, we were doing some optimizations in their workflow, and we realized that the main bottleneck was block encoding. So we spent a lot of time trying to figure out how to reduce the cost of this particular subroutine. So that's the reason, well, I know this topic, I really like to talk about it, and I'm going to divide this presentation in two main parts. In the first one, I'm going to talk about the most famous quantum algorithm for block encoding. Maybe you have heard about LCU or prep cell prep. And I'm going to explain it in a different way. Instead of just showing the algorithm and see that it works, I would like to explain it in the way that any of us could come up with the idea. That I think is a good approach from an educational point of view. And the second half, I'm going to try to talk about block encoding for differential equations. I know it's the main topic for this particular event, so I think it's worth to pay attention to that. So saying that, let's start with the first block. So to start, it's good to know some basic definitions. And the first one is, what is quantum computing, right? There are a lot of different definitions. I choose one that actually fit very well what we are doing here. That is the process of encoding computational problems into quantum circuits, evolving quantum state via unitary operators, and then recovering the classical information through measurements. So as you can see, one of the key words here is encoding. And one of the main examples of that is quantum chemistry. In quantum chemistry, we are going to define the molecules through some objects that we call Hamiltonians. And we think that quantum computing could be a perfect example to find some properties of that molecule, of that particular object. So the first step that we have to do is somehow get that Hamiltonian, that object, and encode it in the quantum computer. So block encoding is going to try to solve one of those problems. So the first question is, well, what is a Hamiltonian? Is from a mathematical point of view, is a Hermitian matrix with a physical meaning. Hermitian means that the matrix is equal to the adjoint of the matrix. Just to confirm, can you see the mouse or you just see the slides?
We do see the mouse.
Yeah. Yes, perfect. Nice. Thank you. So knowing that the Hamiltonian is a matrix and we know that a quantum circuit can be represented as a matrix, we could say, perfect, let's just put the Hamiltonian as the matrix of the quantum circuit. And we could think there should be a gate H that is our Hamiltonian. However, this is not possible. And the reason of that is that all quantum gates that satisfy a property, they should be unitary. And to be unitary means that the inverse of the matrix is equal to the dagger of the matrix. That's important because they have to preserve norms and reversibility. But as you can see, it's not the same property, the Hermitian property over the unitary property, even if they are similar. Therefore, we cannot do this directly in the quantum circuit. So then what people start to do is, okay, let's think in a different ways to encode the Hamiltonian. This is not block encoding, this is a different technique, but I want to give you the context of what people was doing here. And something, a property very cool is that even if H is not unitary, e to the I H, this is going to be unitary. And here I have a short proof of that basically, if we see to this first equality, we know that e to the I, the Hamiltonian, times e to the minus I, the Hamiltonian, is equal to the identity. This is clear because the exponents at 0 and something to the 0 is 1. What that means is that e to the I h minus h is actually the inverse, because it's two things multiply and you get the identity. It means that this is the inverse of this one. And now we can see, okay, what is the dagger of that matrix? So for properties of the exponential, this dagger is equal to the dagger of the exponent. And the dagger of the exponent is, well, dagger means transpose and conjugate. Because it's conjugate, we change the sign of the I, and we just take the dagger of the matrix. And because this is Hermitian, we know that this value is exactly to the same matrix. So we get that the dagger of our initial matrix is minus IH. Because these are the same, it means that the inverse is equal to the dagger. Therefore, we just prove in 2 lines that actually this is always unitary. So what we are going to try to do is we try to encode the Hamiltonian here through this approach, is build this matrix. And without entering details, because again, this is not the main topic of this presentation, this is done through some techniques called product formulas. We are able to approximate this gate, but multiplying more simple gates. And maybe you have heard the name of Trotter, Suzuki Trotter. So those are just product formulas that are ways to create this Hamiltonian. But then researchers started to think there are more ways to encode the information in a circuit that is not through this evolution. And well, someone say, okay, something that we can do is block encoding. So block encoding is this alternative technique to encode the information. And the idea is very simple. As we know, this Hamiltonian is not unitary, but maybe something that we can do is put it as a block, for instance, in the top left, of a bigger matrix, and try to look for some values to put in the other part of the matrix in such a way that now, as a whole, the big matrix is unitary, and therefore we can embed it in the quantum circuit. So this idea is block encoding. So the first question we have to answer here is this always possible? Given any Hamiltonian, there exists values to put here in such a way that as a whole is unitary? Well, it is always possible. And to prove, I decided to choose just one random example where I'm adding these different values in the other parts of the matrix. So I'm not going to enter too much in details, but basically what I'm doing here is calculate the the dagger, and then I multiply them. Because I get the identity, when I multiply them, it means that actually this is the inverse. And that's the reason we just prove that this is unitary, because satisfy this property that the dagger is equal to the inverse. And in practice, these are not the values we are going to put, but I just want to show you that at least we know that is possible. So let's think how we can do that. In the main examples that we do block encoding is when the Hamiltonian is expressed as a linear combination of Pauli words. So the gates Paulis are the ones that we are familiar with, like X, Y, Z, or identity. They are Pauli words. So our Hamiltonian is expressed as a linear combination of those particular words. For instance, here we have an example. We define our Hamiltonian as 1/4 of Z in the first space, one third of X in the second one, minus 1/4 of the product of two Pauli sets. That does, as a result, give us a matrix, this one that we can see here. That matrix is calculated just, again, we just have to calculate the individual matrix of each term and do the linear combination. And these kind of Hamiltonians expressed in this particular way are super, super common in the applications, as we mentioned before, in quantum chemistry. And normally, the number of Pauli words is sparse. There are not too many terms in compared with the size of the space. So this is very useful to work with. So the main algorithm for block encoding is focused in just this particular scenario, when our matrix that we want to block encode is expressed in this particular way. So how we could do that? And again, what we are going to do is try to figure out how we could come up with this idea by ourselves. So the first hint that we can realize is that each term of this Hamiltonian, these Paulis, actually have a circuit representation, because a Pauli have a cool property that is Hermitian, but also unitary. So we know that at least if we just take one of the terms, we can create the particular circuit that apply that gate. We could think in put them together or something, but if we put this gate together, they are going to multiply each other. However, what we are trying to figure it out is how to combine them with additions and some weights. So the first thing to think about, is how we can add things in a quantum circuit. And if we don't know how to do it with operators, something that we know is how to do it with states. So something that we could try is, let's build this particular state. So because we have three coefficients, 1/4, 1/3, 1/4, I'm going to create a state with three basis states, and I choose the three first one in order, 0, 0, 0, 1, 1, 0. I could take whatever. But the important is that I'm able to create this state, and I just codify the coefficients in a quantum circuit. So this is a first step. We now have the coefficients in the computer. Of course, I will have to normalize this, but just to keep the numbers more beautiful, I'm gonna leave it like that. So we are getting closer to our target, to have this Hamiltonian. So the next step could be, okay, I have the coefficients, but somehow I need to say which coefficient goes with which Pauli word. So actually, that's not difficult to do. We can do something like this. To each index, we just do a tensor product in a different register with the particular Pauli, Z0, X1, Z0, Z1. And this kind of index operator approaches is something that we can do through circuits like this. Here, first of all, what we are doing is this prep box, this preparation is going to give us this state. And now what we are saying is, if this is a 0 and this is a 0, apply set in the first register. So that's what we're doing here. If this is a 0 and this is a 0, we have this Pauli. Now, if this is a 0 and this is a 1, apply X in the second one. So we are doing this expression here. And finally, if we are in 1, 0, we have set. So as you can see, this psi sub 2 is really, really close to our Hamiltonian. So we are in a good direction. If we calculate this matrix to see where are we right now, we are get something like this. The reason is a vector is because we have these two projections here starting by 0. But what I want to show is that at least all the coefficients and the Paulis are codified in the quantum circuit. So we are going in the good direction. So now we could check, okay, what we have actually in the top left, because it's the place where we want to encode our Hamiltonian. So the way to check it is just project here with zeros. Basically, the zeros here tell you we take the first column, and here we take the first row. And if we do the math, what we see is that we have in the top left just the first coefficient of the Hamiltonian. So we are still not getting the results that we are expecting. We are improving because we have all the information there, but still this is not a block encoding. So the question that we will have to ask ourselves here is, what kind of operation I could do in such a way that when I apply it, all the information has moved to the first position. And this is something not difficult to realize, that if we multiply this vector by a matrix like this, whatever in different positions, but in the first row, 1, 1, 1, 1, if we do the matrix multiplication, we are see that actually we are moving to the first position the addition of all the column. So here we will have our Hamiltonian. So what kind of matrix, what kind of operation have this particular shape? Well, actually none, because 1, 1, 1 is not unitary. But if we make sure this normalize and we take 1 over 2, 1 over 2, 1 over 2, this matrix is actually just put Hadamard's. If you take Hadamard's and you calculate the matrix, you're going to see that the first row and actually the first column are always 1 over 2, 1 over 2, or dependent of the dimension. That's the reason why we use Hadamard's to create equal superpositions. Because applied to 0, it means in the first column, we have these positive equal amplitudes. So therefore, it means that if here we apply the Hadamard's in the circuit, we are going to create a block encoding of our Hamiltonian. However, here there is an issue. Well, we have the block encoding, so we could be happy with that. But we are adding a factor in front of the Hamiltonian that is going to decrease exponentially with the number of qubits. Here, in our case, n equal 2 is when we get this 1 over 2. But if we have 10 qubits, this is going to be 1 divided square root of 2 to the 10. And that's not ideal, because we are losing the information that we are trying to encode. Therefore, we have to modify somehow this algorithm in such a way that this factor disappears. So here, someone had a really nice idea. Well, again, to clarify this, even if we are talking with vectors, if we remove the zeros, we achieve the block encoding. So this idea was that, okay, what happened if instead of load the coefficients that we have before, we load the square root of the coefficients? If we do that, and it makes sense, sounds like a random idea, but you will see at the end that makes sense. If we do that, we apply the same circuit, and our vector will be this one, 1 over 4, well, square root of the coefficients with the Paulis. But now we have to think, okay, what kind of operator? Now I have to put here in such a way that when I multiply for our vector, I get our Hamiltonian without no coefficient before, without not exponential decay. Well, this is a good moment to stop the video if this is if someone is watching it at other moment. So the solution will be this particular matrix is we don't care about all the values, but in the first row, we are going to put again the square root of the coefficients. And why we do that? Because now when we multiply them, we can see that the multiplication of the square roots actually give us the original values. So we are going to have, well, a square root and a square root. We are going to have 1/4 of z0, 1/3 of x1, and 1/4 of z0, z1. And that's the reason we apply the square roots, because we have to multiply them again to create the original coefficient. And this is one of the main problems, the errors I see people when it's trying to learn this algorithm, that they forget always to calculate the square roots when they try to prepare those particular states, because it's not intuitive if you don't understand the details why I have to do that if I never do that. So I hope that with this intuition that we realize now, you always are going to remember the why you have to do square root, and you get the correct results. So saying that, not all the matrices can be efficiently represented as a sum of Pauli operators, and main example of this is the differential equations. The kind of matrices that we are interested in used to be the diagonal and as the one that we can see here. So we will need to think different approaches to solve this particular block encoding. So saying that, I think it's a good time for solve questions if there are any regarding to the first half. And after that, we can go to the block encoding to apply to these particular problems. Is there any question?
Okay, yeah, thanks a lot, Guillermo. We had a couple of questions in the chat, but Catalina has been kind enough to keep answering them on Discord itself. Let's wait for a couple of minutes. I see some participants typing in, but yeah, I'll let you know if you do have any more questions.
Yeah.
So yeah, maybe this is a good time for a reminder to all the participants. If you do have any questions, please put them on our live chat on our Discord channel, and we can then order them and share them with Guillermo.
Yeah, also at the end we will be solving questions, so also at the end we can answer questions of the first half if you prefer.
Okay, so I do have some questions coming in. Do we need to do amplitude amplification for block encoding?
That's a good question. So it depends the particular application you are using it. But yes, one of the problems of the block encodings used to be that you are adding some constant in front of the Hamiltonian that is going to decrease the probability to get that particular state. When you do block encoding, you are not getting always the information of the Hamiltonian. So in these kind of scenarios is when you have to do amplitude amplification to try to improve the probability of that particular operator. But instead of the typical amplitude amplification, in this particular scenario, the method that we have to call is called oblivious amplitude amplification. So this is a variant of amplitude amplification born for block encoding. So the person who asked the question, I would recommend to read about that particular topic.
Okay, we have a lot of questions coming in now. Another question we had was, okay, why is block encoding essential for simulating Hamiltonian evolution on a quantum computer?
Yeah, so it's QPE, quantum phase estimation, is the main algorithm for a lot of different applications. For instance, if you want to find the ground state of one particular structure of a molecule, you normally use quantum phase estimation. Hamiltonian simulation, the E to the I H, is one way to use quantum phase estimation. But there is another version that is called qubitization-based quantum phase estimation that instead of use Hamiltonian simulation, use block encoding. And it's still not clear when to use one, when to use the other one. Probably they have different regimes. But my personal opinion here is that quantum phase estimation through block encoding is going to be cheaper. that trotter in the long term. So I think we should go, even if it's not the standard algorithm to explain, we should use quantum phase estimation with the block encoding approach.
Got it. We have another question. How do we get the metric with those square roots? And can we do that for any coefficients?
So yeah, so the problem that you have when we are with a molecule in chemistry is that I say always quantum chemistry because it's a very typical example. They give you already the coefficients and the Paulis. So you don't think in the matrix, you think just in what are the coefficients of my linear combination of Paulis and what are the Paulis itself. So that's a list that you have, and you just take the square root. They are not going to be imaginary, and maybe the question comes, okay, what happens if it's negative, right? So there is a small detail that I didn't go in details here, but as you can see here, the initial preparation, that's the square root, and here we keep the negative number. But however, here, I didn't put the negative number. So this will be the preparation of the same state of all the elements possible. So in that way, when you multiply them, you keep the original sign. But the only problem will be with imaginary numbers that, in general, that's something that I don't think even if it's possible, because wouldn't be Hermitian. So we are safe here.
Wonderful. Okay, maybe one last question before we let you continue. Yeah, one of the participants is curious as to why the particular form of state is chosen as phi, and how do we know what's the correct starting point?
I didn't understand. Can you repeat the question, please?
Yeah, why the particular form of state is chosen as phi, and how do we know that that is the correct starting point?
Are you talking about psi here?
Yes. Yeah.
So the only important thing is assign coefficients to basis states. So I could choose perfectly here 0, 0, 1, 1, and 0, 1. Or if I have 5 qubits, could be 0, 0, 0, and 1, 1. So it's not important at all. The only thing that you have to know is exactly what index you have. Because in the select part, this block here, you have to say, okay, for this particular state that basis state that I choose to put the amplitude, put now this gate. So these are not relevant. It's just state preparation of the amplitudes in the basis states that you want.
Maybe I can ask her. So I think the question was more about the fact that it's not normalized. Like, I think that's what is like a few people are asking, like if psi is not phi is not normalized and so on.
Oh, I see. Yeah, we will always have to normalize, and so actually I'm putting here Hamiltonian, but it's always Hamiltonian divide the norm 1 of the Hamiltonian, and this norm 1 appears because we have to normalize these values. So there is always also a prefactor here that I'm not considering, but that prefactor doesn't depend of the number of qubits. It's going to depend of the Hamiltonian itself. But yeah, always we have to normalize. That's I should have choose a better example probably.
Thank you.
No problem. Okay, I'm going to continue then. That at the end you can continue asking with no problem. So what we were saying is that in the case of differential equations, these particular matrices, the diagonal, it means all zeros, but there are some diagonals that we have to put some values, are super important. So in one slide, I'm going to explain what is the case. Even if you are not familiar with differential equations, I think I can convince you. So let's go for it. Imagine that we want to solve in a quantum computer this particular equation. We want to find a function u of x, where x is a value that will go from 0 to 1, such as u of x plus u prime of x equal to 1. That's what we want to solve. Again, this is a simplification. Normally you need boundary conditions, but let's focus just in this toy example. So how we could solve that? The first approach is discretize the variables. So instead of say that x is a continuous from 0 to 1, we are going to do equidistance grid. So we have x1, x2, to xn, where these x sub I are equal to I divided by n. N is the number of terms in the partition. Therefore, what we are going to try to get is not a function u, but the points of u evaluated in our grid. So we want to find u sub 1, 2, n, where u sub I is equal to u evaluated in x sub I. If we have a very small partition, like steps, we are going to get a very accurate solution to the u we are looking for. The next step is somehow remove this derivative because it's a bit difficult to work with that. So we are going to try to approximate that derivative. And how we can do it? Well, by definition, we know that u prime of x is the limit when h tends to 0 of u in x plus h minus u in x minus h divided to h. Normally, this is not the standard definition, but here we are taking a step forward, one backwards, because from a numeric mathematical point of view, this is a bit more accurate. For a small h. So if we choose one particular value, and the one that we are going to choose is 1 divided n, the size of our partition, what we know is that u prime of x sub I is equal to u evaluated in the next point. It means x sub I plus 1 minus u of x sub I minus 1 divided 2 divided n. So we now have a expression of the derivative in terms of our variables that we are looking for. Therefore, we can write the equations based on our variables. We know that ux plus u prime x is equal to 1. Therefore, for all I, u sub I plus the derivative definition that we just calculate is equal to 1. And we know that's true for all the elements of the partition. Therefore, we can organize all the equations in a matrix. And if we organize this in a matrix, we are get something like this, a 3-diagonal matrix. Then here we have the incognitas, the u's, and here all these ones of all the equations. The reason that they appear 3-diagonal and 3 terms is because each of these equations have just 3 variables, and actually they are consecutive, like -1, 0, and 1. And they're going to move if we increase I. So to solve this differential equation is equivalent to solve this system. And here is where quantum computing appears. What we are trying to do is encode this matrix, encode this vector, and then use algorithms like HHL or matrix inversion via quantum signal processing. So different techniques to solve this system in the quantum computer. So that's, in one slide, how it works, more or less. And I was using just that to motivate how important are in this differential equation context these d-diagonal matrices. So let's see how we can encode them, because this is something that we cannot express efficiently with Pauli words. So let's start with the base case, one diagonal block encoding. How we could create an operator like this, where here in the top left, all values are 0, but we can pick some particular values, a sub 0, a sub 1, a sub 2, a sub 3. This particular example is straightforward if you are familiar with operators and the particular matrices. And the thing is that these gates, the multi-control rotation wise, have this matrix. So if we do a control 0 of rotation y, this is the matrix that we get. A cosine of theta in the zeros position, and then all ones, and then, well, other stuff here. If instead of control over 0, 0, we control over 0, 1, the angle theta is going to be in the first position. And we can do that with all the values. Therefore, if we have that in mind, we will just have to concatenate and multiply all the control rotations consecutively. So if in the first case, my angle is arccosine of a sub 0, what I will get in the third position is cosine of arccosine of a sub 0. Therefore, cosine and cosine cancel each other. we are just put here the value that we want. And if we do that with the different indices, we are able to embed this. This particular structure, when we have all the control combinations of rotation wise, is what in the literature we used to call multiplexer or uniform control rotation. And they have cool tricks to compile in a very efficient way. So even if you are seeing right now this with controls in a very beautiful, clear way, in practice, in hardware, is very different. We are able to apply cool tricks. But let's assume that we know with this how to do diagonal block encoding with one limitation. The diagonal have to be in the middle, have to be the main diagonal. So how we could create, again, a base case of one diagonal, but in a different position. And here is where appears the quantum arithmetic. Quantum arithmetic, it was one of those building blocks that we detect in the quantum algorithm toolkit. And without entering the details how it works, I'm going to tell you the behavior that it brings. So if we apply a quantum adder, for instance, of +1 in our block encoding, what is going to happen is that we are going to move to the right one position the diagonal. Is it something easy to check when you know the matrix of the adder? That actually the result is going to be that movement of the diagonal. If we want to move to the left, we will do -1. And we can go to the kth position just with adders. So that's great. We know how to load one diagonal and we can choose the position. So the question is how we can generalize this idea to the diagonal matrices. And also this is a good time for stop the video if you have the chance, because you have now all the ingredients to know how to do it. And now we are going to go to the spoiler. So imagine we want to encode this particular example, this 3-diagonal matrix where we have the diagonal, the next one, and 2 later. So we know that with this multiplexer that normally we represent with this, when you see a circle with a line like in diagonal, we represent all the combinations 0, 0, 0, 1, blah, blah, blah. So with this operator, we do the block encoding of the main diagonal. Then we know that with a +1 of quantum arithmetics and our multiplexer, we can have the second diagonal. And again, if we do a +2 here, we get the third one. And these are circuits that we know independently, but we would like to combine and to add them. And how we can do that? With the algorithm that we see in the first half of the presentation. We are going to do a prep cell prep because we know each individual term, and what we want to do is to add them. To check that it works, it will be something like this. Our initial state, in that case I put it normalized, is going to be the equal superposition of the number of diagonals, 1/3, 1/√3 of 0, 0, +0, 1, +1, 0. Again, you could choose different values if you think it's better. And sometimes it's better. There are less entanglement if you choose a specific basis state, so it's easier to build. But let's assume we take them in order. 0, 0, 0, 1, 1, 0. When we apply the select, this block here, we are saying, okay, if this is a 0 and this is a 0, apply the main diagonal. If this is 0 and this is a 0, we have the main diagonal. If this is a 0 and this is a 1, diagonal 1, and the same with this one. So the vector that we just generated when we start here in 0, 0 is this one. All the diagonals encoded there. Therefore, if we now multiply for the adjoint of the preparation, we are adding here one, this state here. And when we multiply them, what we are getting on the top is the addition of all the diagonals. And because all the values of the diagonals are 0 outside the diagonal, we are going to get exactly the diagonal. Like the addition of one with other are not going to conflict. And that will be the way to encode these matrices using that algorithm. So again, to summarize, after that, what we will do is prepare also this particular state, and again go to HHL or QSBT to do the matrix inversion and solve our differential equations. So to finish with some conclusions, we know that, as I saw you, block encoding is a fundamental block in a lot of different quantum subroutines, and they appear very natural in quantum chemistry because the molecules have a very simple Pauli representation, and in differential equations, because of these techniques to do the diagonal block encodings, super important, different inputs require different methods. There is not one that solves all of those. As you can see, we have different approaches for these two applications that we have mentioned. And finally, this is an active area of research. This is not a solved problem. We are continue working and trying to find better methods because it's something that appears everywhere. So thank you very much, and happy to answer more questions.
Okay, wonderful. Thanks a lot, Guillermo. Let me bring up the Discord chat again. See if we have more questions, and we have a lot of them. Okay, wonderful. Okay, so here's a good one. Why would we require to use discretization for employing block encoding? Like, for example, is it possible to have multiple overlapping continuous intervals, or would that be a problem?
So I would say that in the moment that you think in the quantum computer, always you have to discretize. You cannot work with this continuous thing. But the cool thing is that if you add the size of the grid increase exponentially with the number of qubits. So you can be really, really accurate, but just adding a few qubits. So I will say, even if we are thinking in the discrete version, is going to be very continuous-like.
Sure. Let me just scroll through these questions to find a good one for you.
We can go, because somebody asked, this looks hard to do by hand. So how do you do it? I know that we have the tools for that, but maybe you can recommend some.
Yeah, in PennyLane, if you are coming from the size of LCU, for instance, like you have a linear combination of Paulis, it's very easy to create a Hamiltonian outside your circuit. You have your coefficients, you have your Paulis in a list, so you have the object, and there is a template called qml.prep cell prep that you just have to say, okay, this is my Hamiltonian, and it's going to work everything under the hood. For the case of the diagonal block encoding, we don't have right now the implementation for that, but the fact that you have prep and select also as different blocks, I think is going to make your life easier. So I would recommend anyway to try by hand, because it's always the way to learn. And in the future, we will have probably support also for the diagonals matrices.
Oh, wonderful. Ken, there's a doubt on your last slide. So if you could explain the last quantum circuit a little bit in more detail, especially what that bubble and the slash in it mean.
This circuit, I guess. Okay, so here, what we saw before is that, well, let me go to the original one. Okay, so here what we're saying is, if we want to do the addition of this Hamiltonian, we need 3 parts. First of all, a part that prepare the state, well, this one. Then a second block that is select, that create the particular unitaries that go with each coefficient, because set is Hamiltonian, but is also is Hermitian and is also unitary. So this part assign the indices with the unitaries, and then prep adjoint to compensate the square root. So here, what we are doing is exactly the same. Prep, because we want to add the 4 diagonals, we have this equal superposition. And then what we control is over the unitary that goes with that index. So this gate in blue is just the circuit that prepare the diagonal in the middle. The green circuit is the one that prepares the unitary that block encode the diagonal in the second position, because this is main diagonal, but this is the operation other plus 1 that we see that in arithmetic, the other is the one that moved to the position that we want. And finally, this third circuit is saying that in the index 1, 0, we put the unitary that block encodes the diagonal in the third position. So these are the diagonals, and the prep adjoint is to combine them in the top left of the map.
Okay. So yeah, on to the next question. Yeah, there's a question like, the participants have learned some encoding techniques in the past. So are angle encoding, computational basis encoding, these kind of encodings related to block encoding? Like, what are the key differences in their purpose, implementation, or application?
Yeah, so all that maybe motor and state preparation, angle encoding, this basis stuff are techniques to encode vectors somehow. Block encoding is a way to encode matrices. So that's the main difference. Are different ways to do it. Normally, in those methods, for instance, the angle encoding, you lose a bit the track of how the vector is added in the circuit, because you start to have all these tensor products, so it's not so easy to visualize. The cool thing about block encoding is that it's super clear. You know your matrix is there in the top left, so it's easier to work with that. So answering the question, one is focused in embed vectors, this in embed matrices.
Perfect. And maybe a follow-up question here would be, how many types or how many varieties of block encoding techniques are there for molecular Hamiltonian?
It depends. So there are a lot, and normally this prep cell prep is not the one we use. There is something that we call, well, internally we put it that name, like smart selects. So right now the preparation and the selections are very independent pieces. But there are techniques that they make sure that they are built together in such a way that you can reduce the cost a lot. And also, it depends of the kind of Hamiltonian. For instance, in chemistry, there is a lot of symmetries. And you know that if this coefficient and this Pauli word appears here, the negative is going to appear in a different place. So you can encode in such a way that you just need to prepare one, and then maybe with a Hadamard or with something split in the two. So there is always some little tricks that you can do, and a lot of literature there.
For sure. Okay, this next question goes back to the previous slide. Can you explain why there is a 0 at the bottom of these matrices?
When there is a 0, sorry, where?
Yeah, probably this one. I'm not sure if the participant can clarify maybe. The question is, can you explain why there is a 0 at the bottom of the matrices?
Oh, okay. So maybe, so yeah, normally, actually, this is not just tridiagonal, and it's going to appear some terms in this corner. This is something that we can see here. If we have this diagonal and we apply the other, the B3 is going to go here. It's not just a 0. So assuming that's the question, the thing is that we are just interested in the diagonal matrices. This is something that is not helpful to us. So what we can do is just choose that value to be 0. So when we are doing this particular block encoding in the last B, you can choose the value. So you can force to have the D diagonals. But if you don't do that, they're going to appear some terms in the bottom left. If that's not the question, you can reformulate letters and we can try to figure it out.
Yeah, they mean it for the 1x4 matrix, which you shared.
The 1x4? Not sure which one. I don't know what matrix are you talking about.
Okay, yeah, maybe we can hold on for this question for the time being. But yeah, we'll some of these questions, and we can share them with you over email as well. So whenever you get time, you can share back your answers.
Yeah, also feel free to contact me, probably LinkedIn. I used to take a look. So you look for Guilermo Alonso-Linaje and feel free to connect.
Wonderful. Yeah, that's amazing. Also, for all the participants, Catalina from Xanadu is pretty active on Discord. So you should find her in the chat as well. So if there are any particular questions that are bugging you, she is also a very good person to ask. I see a few more participants typing up in the chat, but I'm assuming these are more of discussions rather than specific questions. Like the chat is pretty active right now. So yeah, maybe we can start wrapping up the session today. Yep. Okay. Yeah. Thanks a lot, Guillermo. This was really fun. Thank you for the interactive session, and for all the participants. Thanks a lot, everyone, for being here today. We'll all meet on Monday for another session by Xanadu. So yeah, really excited for that. For all the participants, if you did not catch up our Wednesday sessions, I would highly recommend those two. We had a very interactive lab tour. Lab tours are something which are way less common than these lectures, and we make a lot of efforts to put these and bring these lab tours for all of you. So definitely watch that session. And we also had a pretty interesting session on Wednesday with a lot of CEOs with different quantum startups with the Elevate Quantum region. So if any one of you is interested in starting their own startup or building something in the quantum space, I would again recommend all of you to watch that. One final point I would like to mention are the projects, which would be announced next week. July 1st, we'll be announcing 3 projects for all of you. So stay tuned for that as well. And with that, I think this is a good time to start wrapping up. I'll still be around for any more questions, so please feel free to bring the questions on Discord. But otherwise, yeah, have a great day. Have a really good weekend, and see you all on Monday. Thank you, everyone.
Thank you very much.